com a gente! Nós somos um time feito de pesquisadores e de pessoas com deficiência.
Siamo in competizione l'uno con l'altro.
우리는 흔들리지 않는 신념으로
Wir teilen Emotionen, Spaß und eine gemeinsame Vision.
Wir stehen für Inklusion und Diversität.
모두에게 주어지는 동등한 기회와 권리.
우리는 그 당연한 진리를 지지합니다.
Pari diritti e pari opportunità per tutti.
Für mich persönlich ist CYBATHLON bis heute die Erfahrung meines Lebens.
Es ist der Sieg!
Wer Teil vom CYBATHLON?
Porque através do CYBATHLON você pode melhorar a sua vida e melhorar a vida de outras pessoas através do seu exemplo. Junte-se a nós!
Mach mit! Wer Teil vom CYBATHLON 2024.
We would like to welcome our audience here in Zurich, as well as our audience online, to the 5th CYBATHLON lecture of this fall. I'm Julia Amos, and I'm the head of discipline of the Vision Assistance Race at CYBATHLON. Teams all over the world are currently preparing for the CYBATHLON 2024, which will be taking place next October. On the road to the next CYBATHLON, we are organizing different events for our community. One of them is the CYBATHLON lecture series. For this lecture series, we asked our current as well as potential future CYBATHLON teams what topics they would be interested in. For these topics, we invited selected speakers to give a talk. In the last couple of weeks, we already had 4 different talks on different topics. In case you missed them and you would like to rewatch them, you can access them on our website. Today, I'm excited to welcome Cesar Cadena to tell us more about how machine learning and artificial intelligence can help to improve assistive technologies. Cesar is a senior scientist at the Institute of Robotics and Intelligent Systems at ETH Zurich. There, he leads a group at the Robotic Systems Lab. Additionally, he holds a position as a managing director and is responsible for education at the Robotic X initiative of ETH Zurich. With this background, he is the perfect speaker to tell us more about the limitations and opportunities of machine scene understanding in assistive technologies. Before we start the lecture, I would like to remind our audience on Zoom that they can use the Q&A function to ask questions. We will then address these questions after the lecture with Cesar. With that, thank you again for being here today, and I'm looking forward to hearing more from Cesar.
Thank you very much for the kind introduction. Then, hello everyone. Today, as mentioned, we are going to talk about a little bit about machine scene understanding. I will give some opinions about the limitations that you will find on it and some opportunities that I think are very relevant for CYBATHLON. Some of the things that I want to start with is giving a context or giving a setup. Where are we in this talk? What are you going to see? Then we are going to visit some concepts of machine perception, but this is not a tutorial. You will not learn machine perception here. There are lectures for that, whole master programs for that. All my opinions are recommendations around CYBATHLON 2024 competition, checking what are the tasks, what are the challenges, and trying to accommodate what would be useful for you in case you want to take this message. It's more in the line of practical points for your competition, for your team, more than long-term research questions. This is not a research talk. Saying that, I want to also give a disclaimer. First, I'm going to present here works, some from my team, some are not mine, and I don't want to take any ownership of those works. I just use them to illustrate a point, give you a vision of a system, or transmit a concept. Images and videos that you will see here are taken from those papers, from these authors, from their channels, or third parties that are have implemented those systems. Also, you will see some images that are taken directly from the book of rules of CYBATHLON, and also from the website, just to illustrate what we are talking about. Then, in the context of the CYBATHLON races, then I go there and check what are all the competitions that you have. We have 8 competitions here, right? And then I have tried to check in all of them where are the perception or sensing words mentioned, or where it could be used as a machine perception or scene understanding. If we go for the 3 first on the left, BCI, the wheelchair assistance, or the functional electric simulation, there is almost none. It could be used, but there is nothing in the challenge that we could say directly applicable. Then if we go for the processes, yes, we see something that it could be like if we could help if we have some sensory feedback, maybe touch, haptic sensing, or maybe the joints. In this talk, I will not refer to those sensing capabilities. Then we have the exoskeleton race, right? And then we see there that if we have some kind of sensing that could perceive the situation around the exoskeleton, it could adapt to those movements, the movements to this terrain or the different situations. That would be great. Probably some of the things that I am going to mention today would be helpful. Finally, we have the vision assistant race and the assistance robot race. On those ones is where it's more applicable what you are going to see today. Then we have different words here, different keywords, is reliable substitution of vision, spatial orientation, mobility, recognition of context for a task, obstacle avoidance, and also dynamic elements. More in the robot part, we have manipulation, and for that manipulation, we also need to do some recognition as well as some navigation, avoiding obstacles, as well with dynamic elements. Probably the teams working on those last 2 will benefit the most from today. Then let me start by explaining what is machine scene understanding, or giving you a couple of examples of what is inside machine scene understanding. I'm talking here about machine scene understanding and not robotic scene understanding, because you are not obligated to use a mobile robot to perform your challenges. You can use an iPhone, a smartphone, a tablet, you can use anything that is not necessarily called robot. Then that is why we are going to say machine scene understanding. Then in machine scene understanding, I'm putting 2 examples here. One where there is an entity outside of the person that needs the help, the assistance, and the other one where the agent, the person that needs assistance, is inside the entity. For performing the task in a proper manner, these agents will need a spatial perception. There is a spatial perception is split between localization and mapping. What is that? That means that these agents need to know what is the metric location of things around them. What are the obstacles? How far are the obstacles? How far is the object that I need to manipulate? What are the dimensions for that? Same that you probably need to know what are the obstacles, how far are the obstacles, and how far you need to take decisions given a respective traffic lights. Given this information, you are able also to locate or to move in these environments, right? That is the localization part. Now, that is not enough. Just knowing the metrics, the distances, is not enough. We need also to know a little bit more of higher level, semantic perception. Semantic perception is many things. Some of them is the categorization problem, categorize, classify what we have around us, is affordance recognition, recognizing what can be grasped, what can be citable, what can be movable. Or action recognition, just to recognize what is happening around. Then in categorization, we probably need to recognize people around us and the people that actually we need to assist. We need to know the support geometries that are around. Where can I place the things, where you can sit. What are you going to do in this situation? Are you going to drink? Are you going to write? What do you need for performing the action? And also, what is around me? If I have to look for something, where should I look for? The same happens in the example on the right. Very likely, if you are in a traffic scene, you need to find or be aware of the traffic signs that are around you. You need to know where can you navigate, where can you walk or be over. And then you need to know also what are the other agents' movements and who are those agents, as well as read the obstacles or where do you have to pay attention to look for a coffee shop, library, so on, right? All of that information goes inside the semantic perception, which is huge. It's a lot of stuff that we have to do. Let me start by the geometric part. Let's say the easy one, right? The easy one, we will see how much. Then spatial perception, as I mentioned, is something about recognizing what is around us in distances and how do I move in that environment. Then let's have an exercise. We have an observation. This is a general observation. It could be an image. It could be the point cloud from a range sensor. It could be even an event-based camera. I actually pick it up just to be agnostic. This applies for any of the sensors. Now, the machine will see this, doesn't know anything about the environment, but it will continue seeing something that is changing. Those observations are updated, right? And with that, it has to infer how it's moving around and what are the distance to these obstacles. It's kind of tricky. Let's try to do it a little bit slower. We have an observation in time t. And then if we define a frame of reference and a position or pose for our agent in time 0, time t equals 0, that is going to be our initial position. Then now we can go and move and receive our second observation, t plus 1. From those two observations, what I can do is try to find what can I recognize from one frame, from one observation to the other. Maybe some corners. Then I can say, OK, these corners are similar. You know, this seems a point that I have seen before. And then I can do these matches, these correspondences. Having that information, these correspondences of how my observations are changing, then I know what is the error that I can make to transform one observation into the other. To transform one observation into the other is what is going to allow us to compute our next position, the one that from where we observe t plus 1. With that, then we have a pause, and we go for the next observation, do the same, and then move in the world. Now, with that, we are estimating our trajectory, our position. If we repeat the same that we did a couple of slides before, then we have a sequence of observations, right? And you know that now we are tracking these repetitive points or things that we can recognize. And then that will give us, in our initial frame of references, our trajectory. This is called motion estimation. You can call it state estimation, odometry, or ego motion. All of them are referring to the same. Let's call it odometry for the next slides. And then in the initial frame of reference, time 0, you will have then your trajectory that is depicted here, that maybe was inside that door, I think it's a door, and go up some stairs. OK, that is very basic. But of course, that is not the state of the art, right? Then let's see how this is working in reality. What can you do when you go outside and go look on the internet, in the library, the best methods to do this. You go, and you can go online and check for a state estimation that use features like pointed here, this is a feature base that is doing exactly what we say. 2 frames, finding correspondences, and then finding what is the motion that generated those that explain these correspondences. This way of doing in feature base, you need to process data in 2 different time steps that we know, and you use a few data points. Probably those data points need to be more informative. Compute a description just that you are able to say that 2 data points are corresponding between 2 observations. If you use images, like the case on the left, probably you are minimizing a reprojection error. What is that? Is you find the rotation translation, that is your pose, rotation translation that minimizes that error that is on this equation. And this is the most of the equations that you are going to see in this lecture. You can also do exactly the same for point clouds, range sensors. And what you are doing is computing these points, finding the correspondences as we were saying, and finding rotation translation that minimizes that error. The same. It's the same concept for both. Now, this is with features. You detect something that you are able to track over the observations. Now, there is another way to do it, and it's called direct-based or featureless. We don't compute exactly the features, but we use raw data. If we are in images, we use just all the pixels or most of the pixels that you see in the image. Then, if you do that, then we have more data points, but each one of those data points is probably less informative. We are going to use as an information only the intensity, probably in images. And like that, then we will minimize not a reprojection error, but a photometric error, the difference between intensities of those 2 points that you say that they are the same. Again, this is in images, but you can also do it in point clouds, in range sensors. And it's doing exactly the same. Of course, here we don't have intensity of the point cloud, of the range, but we have the 3D position. And what we minimize is that those distances between those 2 points that you say that are the same, it should be 0, right? That is the minimization that we are doing here. With that, we are computing our odometry, incrementally computing our motion. That is all fine for the motion, but as you can see, you were seeing in the videos, they give you different representations. Some of them were giving you points in the space. Others were giving you like a more dense, you could see objects there. And that has to be with how you choose to represent the world around you. Then those are the representations, and we can try to see what representations we use in robotics, in spatial perception. We have one line that is topological. Nodes, like places could be, and what is the relation between those nodes. And a clear example of that is tram stop. When you go to the tram and look at the map of the trams, then you will see that you have ETH there, and then if you take the line blue, then you can go to handleback, and then you will find all the relations there. But that is not metric. That only gives you neighboring, or I can achieve, or I can reach a node from a different node. In the metric side, it's more similar to a floor plan, if you can imagine. A floor plan of a building. How those metrics are subdivided, we will have, if you use, for example, feature-based that we were thinking before, we were seeing before, you can have sparse representations. You have a point cloud, you have the trajectory of your agent inside, and you have this point cloud that it's just points here and there. You can go for the other side, a little bit more dense. Then usually the featureless, the direct-based methods will provide you more information. And those are the ones that you will, at least for the human, will perceive more as a recognizable objects. If you go not only for the dense, there's a subdivision that is still volumetric. And the volumetric representation doesn't give you not only what is occupied, but also tells you what is unoccupied explicitly in your representation, and also what you don't know, you haven't ever observed. And those representations have implications for you. Some of these implications, let's see them here, because there is also a taxonomy to be drawn from the dense representations. And they will give us, or is determined by how the geometries encode and whether they represent continuity in the structures in the surface, or whether they also represent the free or the unknown space. Then we have two sides. One is explicit representations. We have points, as we saw before, or we could have even a little bit more high level. Points, not only points, but also the normals and the area that that point is occupying. That is called surface, as seen here. You can also go for the other side of meshes, where actually you have points, but you have connectivity between the points. Those are created meshes. If we go for the other side, that we call implicit representations, we can have occupancy. Occupancy, as you see here, you have two objects, this triangle and this square, that are the real objects. And if you navigate around in the white, you will see what is free space. In black, you will see what is observed and then is occupied. And behind the gray part that you don't see is the unknown. Explicitly, you encode that in your map. But you are not encoding what is a surface. The information is there, but you are not explicitly encoding as you are doing in meshes. Then that from there is that you call it implicit. Another way to do this is with sign distance fields, where instead of just saying 0, 1, occupy, not occupy, you encode what is the distance to your closest obstacle. Okay. If we see that, now let's try to see some examples, what we can find. What can we go download and run in our machines or in our phones to start doing this and be useful for us? Then you can go and try to do OrbSlam tree. It's a very good technique, very easy to use, very robust. Or you can go for sparse direct odometry from TU Munich, and it's a direct-based method. As you see, the accuracies are pretty good. You see the trajectories of the vehicles, of the agents, but what can you tell me about the regions that they don't have points? If you see here, for example, the computer screen, you have all the edges, but what is in the middle? Is empty or not? We don't know. As a humans, we infer very quickly what is it. But as a machine, it could be something tricky. We can go for denser representations, maybe with surface. We were talking, and you have examples like elastic fusion. You can also go find it online. And you will find that those representations give you much more information, and you think that, you know, I could navigate there. I will know all my obstacles, no problem. Or you can go to something like a wildcat that generates kilometers scale environments almost in real time. As I mentioned, because they are denser, probably they are very useful for obstacle avoidance, right, or manipulation. But still, surfaces are an unordered set of points. Then it's not easy to query if one point in the space is occupied to know which one is the next one to it that is occupied or not. For that, we will have volumetric representations, right? On the left, you have box blocks, that is a grid base, or on the right, you have waymap, that is an O3, is a little bit more efficient in memory, just because it is hierarchical. And you can see how that represents the world. And the important thing there is that you don't only have the world and all these dense knowledge to manipulate or to avoid obstacles, but also what is free and what not. That allows you to perhaps perform motion planning, or to know what is a structural continuity of the surface continuity. Then when you query one point and it's occupied, because of how it's encoded, you will know which one to query to see if it's occupied or not. Let me talk about limitations so far in this spatial part. All the methods that you have seen, that we have talked about, they have an assumption is that the sensor is the only moving entity. The visual sensor, the range sensor, is the only moving entity. That means that if you have a lot of dynamics around you, probably you will have problems. And you have to be aware of that. Some of these methods are robust to some dynamics, but you have to test and check how robust, to what extent of those dynamics. In terms of change, the same. The surroundings of in the sensed modality are also not changing. What I mean by that, for example, the illumination in the visual sensors is not changing. If you are here and you turn off and on the light all the time, most of these methods are going to just fail, right? Then you have to be aware as well how much illumination can be changed gradually. This is in the visual sensors. You could also think about the same changes structurally for the range sensors, like dust, fog, air particulates. And finally, in this slide to mention is that every sensor or sensing modality and also every representation, they all have disadvantages. And it's better that you know what are those ones, right? And you don't know those ones until you don't try or check them out. For example, if you have a range sensor, a LiDAR, and you see only the structure, and you go in a long tunnel, and you try to do this motion estimation, compute this odometry, you will fail. For the simple fact that in the long tunnel, everything is the same, doesn't matter where you move in the tunnel. Then you don't know if you move 1 meter, 10 meters, 1 kilometer, right? Maybe you need to go for another approach that combines this 3D geometry or the range sensing with something like the reflectance of the surfaces. Maybe you pick something in the environment that allows you to compute this motion. This is actually one tunnel here in Zurich that is very famous for the bicycles. Those are in the sensing part. But the representations, as I say, also have the disadvantages. It's better that you try out and start to know what are those. For example, on the left, you have a direct-based method, give you returns, then give you the map, more or less in every place that you have a gradient or an edge. And it's fine, but you know that you actually don't have any return on the floor. Then you don't know where is the floor, right? You should have some edges. Maybe you can extrapolate and compute a plane. I don't know, but there is empty space. Same happened with the feature base of SLAM. And in SLAM, you have to be aware that it's not every edge, right? These points are more scattered. Then how do you use that information for a downstream task is something that you have to learn or be aware. If we go for volumetric representations, the same. We have to try out and see, okay, you know, I put Super 8 in this on the left, this a framework that you put the grid resolution to represent in 2.5 centimeters. 2.5 centimeters, and I am losing all the legs of the table. Maybe not the best if you want to avoid those, right? I mean, there is a rule in the CYBATHLON Racing rules that if you touch one branch, you are done. You are out of the competition. You don't want that. And if you use web map, okay, you have it, but yes, 5 centimeters, maybe it's better. what happens if I go 2.5 centimeters? Maybe I even see more details on the table. I don't know. But all of these things, you will not know until you try. Okay? With that part, I will move on to the semantic perception part. As I was mentioning at the beginning, semantics encompasses many things. We have people detection, object detection in the wild, semantic segmentation, what is a building, what is the ground, panoptic, or identify different instances of cars, people. Even in 3D, how do we accumulate all that information, or how do we recognize in 3D? And to the point of, can we just ask questions, and the system reply to us with an answer? Is this visual question answering techniques, or action recognition, and even draw, or that tell us, the machine, how do we perform at the given action, right? Like, how do I make coffee? And give me the plan, right? There's many things in semantic perception. Now, the common thing in all of them is that they are powered by data, and a lot of data. Some years ago, you were thinking, okay, 20,000 images. In 2016, is wow, it's a lot, enough. But you go 1 year later, and no, 20,000 is nothing. You have to go for the 200K, 200,000, or 7 million, or 3,000 videos for action recognition, or terabytes and terabytes of data. And what has been proven in all of these techniques in the deep learning era, the 2020, is that more data, the better. You get more accurate, you get better, right? Then we cannot limit ourselves. That draws more or less how a typical pipeline in semantic perception or in machine learning would work. The first thing is that, of course, you have to propose a model to solve a task. And what you want to do is to go there and find all possible data that you can use to train that model. Train that model performing one task or several tasks or as many as you want, but such that you have access to the most of the information of those datasets, that you can harvest all those datasets. That will be your training part, you learn a model. Or somebody, one of the big ones, companies, maybe train a model for you because they have the TPUs, the GPUs, the clusters to do it in months that you probably don't have access. But if somebody did, then you go, take that model, take data for your particular task, some small data set, and fine-tune that model for you, for your competition, for your task. And then finally, you go and deploy. One input, model, give me the answer, right? Typical pipeline of machine learning, and you can do this for endless tasks and even make businesses out of it, right? Let's see how that works. I mean, in general, just the pre-training, just training, not even in a particular task, works reasonably well, and it could be even useful, right? We can just send it here. This is a method, segment anything model, SAM, and you give an image and then give you segments of what is in there. Then you can use it already just to separate different instances in your cover, maybe how many things are hanging. Maybe you can already count there very quickly. Or, oh, I know that I'm in a path. Where is the path extending, right? Without doing anything else more than taking the trained model. Or, all these chairs, how many are there? And I can see already where are people and not, or any other segment that doesn't belong to chairs, and know if they are free, right? No fine-tuning, it works. It's good. But, okay, let's try something that is a little bit more 3D, combined with the spatial perception. You can use an object detector, a mask-based one. There's mask RCNN that is based, on the left, here, and is painting the dense reconstruction, in this case, Earth's surface. Sorry, this is Super 8. Then here, these boxes are painted by what has been detected, and then you just use it. Still no fine-tuning at all, not changing the task. You just download a model. Similar happen on the right. You are detecting with mass RCNN objects, and everything that has not been detected there can be segmented with the depth camera, and then you have a more dense representation of all your work, right? Still, you didn't change anything in the semantic perception more than acquire that data and combine it with the 3D. Now, you could do that alone, but you could also put it there and put it more in a particular task. In this task, what we are doing is you have your reconstruction of the world, but this reconstruction of the world is not monolithic. It's not a monolithic reconstruction, it's a reconstruction that is driven by the semantic perception. What that means is that if you detect a sofa, the sofa is reconstructed in its own and lives in the space, in the storage space as its own. Is a sofa, a chair, a cup, the walls. That allows you to do different tasks, like in this paper, exactly was change detection. Today you have one configuration in your apartment, next day you come and something has changed and you just want to query what has moved, and will tell you, sofa is not here, sofa is there, the full object in total, right? Now, if we go more for the fine-tuning part, we download these models that they are very, very good in giving us some information about what we are seeing. We take one of those, and at the beginning, if you notice on the right, the left bottom image was totally blue because we didn't know anything. By a few iterations where the operator is driving the robot around, then the robot is labeling the work, saying like, I can step here, this is traversable. This is the fine-tuning. Then in an online manner, you are changing the model such that now it says, you know, I see this, I know where can I go, and I know what are going to be obstacles, and I cannot step in. It's just computing the traversability online. And will adapt to any other environment. Then you don't need huge training data sets in the forest. You just deploy a little bit and fine-tune a big model, right? But that is not all, right? Now, if you go online, there is a very cool demo. Here is the link. You can also give an image of a task that you have to perform and ask, I want ketchup. Is there ketchup? Say, yes. That is the answer of the machine. You say, OK, maybe I cannot see it. Find it. Then it will tell you, probably you don't see it very well, the red square here is not exactly marking 1, but I would say good enough. Good enough to go closer and ask the question again. Or another example, you have all your t-shirts, right? And say, I need a white t-shirt. You have to tell me where, right? It's very difficult by just touch to know. You say, OK, you know, your white t-shirt is there, or the closest to white, right? And you can use it directly. Works reasonably well. Still, we will have some limitations there. If you think about the progress in machine learning, in perception, has been possible thanks to 2 things. And those 2 things are also part of the limitations. First is data hungry, consumes a lot of data to have good models. Even if you fine-tune, if you have more data to fine-tune, you will get better. But you can never collect all the data in the world. And it's computationally heavy. to train the big models, the more accurate models, the best performance models, you need a lot of computation that we don't have. And when you deploy the things on the edge, on a phone or on a robot, you have, yes, you maybe have a GPU there, but it's limited. You cannot put the biggest possible models. That is why a lot of things you run on the cloud and you have to query all the time, then you have to be connected to internet and to get those performance, right? One big limitation to mention is that there is no magic here. There is no intelligence searching in the machines here. This is just a query to check if it's in the database or was trained in that database. If it was not in the training data, most likely you will fail. Okay? This is not just something from me. This is a snapshot of a talk in 2020 by Andrei Karpatik. He was at that moment, I don't know now what is his position, but was in Tesla as the person driving the perception side for the autonomous driving, and was showing examples of, it's an amazing talk where he showed examples of where these things fail in the real world, in autonomous driving. Where do you think, of course, if you have these traffic cones and they just fell for some reason, now you confuse them like traffic lights. Or you have this mirror in the car in front, then you always think that it's something different, that the road is empty and you can go pass by. Who will imagine that the chair will fall from there, right? Then it's impossible to cover all the details in the data sets, in the training data set, and then you have to be aware of that. Examples of that, you don't have to go to autonomous driving. You can just start walking in Zurich in one big winter, like 2 years ago, if I'm not mistaken, January. Start February, maybe, close to my place. And you walk and what do you recognize there? And then you send it to this amazing framework about segmentation. It's still doing the segmentation, but then it starts confusing things. And part of that was a pedestrian walk. It's also part of the same that is a road. Then you can start having problems just because this data was not close to the training data sets, right? Or you can start seeing very unexpected behaviors where it's very critical or very dangerous. For example, you go with your image and say, like, I want that you describe this image. And the description that the machine gives you is that there is a person, because there is a hand, of course, that is in a white chair with blue jeans and is touching a computer screen. That part is correct. And there is a picture of drinks, which is also correct. Then you start seeing mistakes, right, that you don't know from where. Then think, okay, let's be more specific, right? I know that I am in a coffee shop or in a restaurant, and then I say, okay, please locate the steak option in the panel. The steak option is there, right? It's a pizza, steak, pasta, dessert. Where's the menu on the left, right? You would imagine that it's able to recognize steaks. Say, yeah, something else is a steak option. Then you click there, and you don't receive a steak, right? It's bad. But maybe we are asking too much to the machine. We have to adapt ourselves. Locate the black coffee option in the panel, right? And that will be easy to do. Then we do it. We say, our user receives a mocha instead of a black coffee, right? Then the message here is you have a very powerful tool, but it's a tool that you have to get to know because it can have a lot of mistakes. And you have to be able to recognize those mistakes. Then I want to go now, concluding with the possible opportunities that I see. This covers both sides. Spatial perception and semantic perception is in general for machine scene understanding. The first one is you have to think really when do you want to have these complicated methods, or not that complicated, that you can still run on the phone, about motion estimation, how to represent the map, how to represent the environment, sparse, dense, or when do you want to go and say, let's go simpler and remember how the parking assistance was working in the past. It was just a sound saying something is close, that's it. And then later evolved on left, right, behind, where is something close. And then now we have this visual feedback that we know everything around our car when we are parking, right? Then maybe you want to go back and just be very reactive with local behaviors. I don't know. You have to check that. Something that has resonated over the last talks, in the first talk from Christian, he was highlighting this, and it's very important. You need to test anything that you are doing, whatever you are doing, in an environment that is as similar as possible to the place where you want to deploy. You cannot have exactly the same, but you have to be aware that you have to be close enough. Close enough to, for example, you are not in the lab that everybody is going to be static and looking at the thing happening, and that's it. No, you are in a competition race, right? There is a lot of public, a lot of spectators. Maybe they are moving. Maybe other people is moving, other teams are moving around. You have to account for that, right? You have also to have in mind the scale or where you are testing. Especially for the motion estimation and representing the map, that is very important to know if something is close, because if I move a little bit, give me a huge hint about my orientation, how did I move, or if something is far away, and I think that I'm going to do the same, if it's far away, is, you know, the sun, a tree 2 kilometers away, and I move a little bit, that doesn't give me any clue of motion. Then you have been fine-tuning everything in your system, and you come to the grand arena, it's much bigger than your lab, and nothing is working, right? Then be aware of those things. And if you are able to get your own data, that could make a difference for data-driven approaches, for machine learning approaches, right? Now, those are general opportunities, but I think the biggest opportunity that you have to exploit, that you have in your hand, is not in the machine, and it's something that has been also mentioned in several of the lectures before. Your pilot is your biggest asset. Overfit to your pilot's skill and to the race. Involve your pilot with any technology that you want to choose to use, with a sparse representation, dense representation, doesn't matter. Just involve your pilot that knows what you are doing, and knows, the pilot knows if he can understand and how he's going to understand those technologies. That is one part of the system showing to the pilot, but also you should train your pilot. That is my opinion. And that is going in the way of what is the typical systems outcome and what is the typical mistakes. And to illustrate that point, I want to go to the robotic vacuum cleaner human adoption. This is the vacuum cleaner, robotic vacuum cleaner is probably the robot that is the most widespread in the world. Millions of those are in homes, okay? But I will change something here. More than adoption is human adaptation. We come with the dream that a robotic vacuum cleaner comes and cleans our place. And then you realize that, oh, you cannot lift cables around. Or some kind of dirt is not possible to clean. Or, you know, you can have accidents with your hair, right? Then humans started to understand what are the limitations of the technology, what are the typical mistakes, and the first thing that you are doing when you are deploying your robotic vacuum cleaner is picking up everything. And then you turn on the robotic vacuum cleaner, right? It's good to pick up some dust. It's not good to tidy up your place, right? Then you adapt yourself to that. Then your pilot needs to do the same. And you will get the best of the technology, because there is no magic here, if only if your pilot can adapt the reasoning and know this is a typical mistake, I don't trust that, or this is a trustable outcome. And of course, if possible, use your pilot's input to fine-tune your systems, to modify thresholds in your systems, like it's too close, too far. What do I need to use, or what parameters do I need to change? Try to use your pilot from the beginning on. With that, I want to thank you all, and thanks CYBATHLON team for inviting me, and I hope that some of the messages are helpful for your competition. Thank you.
Thank you very much, Cesar, for your nice talk. It was very interesting, and I think we all learned a lot. So now we're going to go over to the Q&A and ask you a few questions. Maybe I can start with the first question. You mentioned that there's a spatial perception, and then there's the semantic perception where you classify the edges that you detect in the first step. Are there any applications where you only base yourself on the edges detected in the spatial perception, or is it always needed to classify it?
No, there are. The first application that you can think is when you don't need to reason or you don't want to do anything with that environment. Then edges, detecting edges and moving around is just very good to tell me where am I, and then where am I in, or how much I'm moving. And a typical application of that would be like if you don't have GPS signal in your car, you can have that system and just know I am advancing 1 kilometer or I'm advancing at 30 kilometers per hour. That would be enough. But that is only for the sake of moving around.
Makes sense, thank you. Are there any more questions from the audience? Yes.
So I also have a question to the concept of semantic perception. So if you compare the CYBATHLON competition with the real life, so in the CYBATHLON everything is defined, but maybe you don't have the data sets because it's kind of an abstract scenario, even though mimicking the real life scenario. So is it then a new challenge or for these concepts, or to apply this concept, or is it more easy because everything is defined, or would you even go for other solutions, add other concepts?
I don't think it's or more challenging or less challenging. I think it's just another challenge. In any of the applications of machine perception, in semantic perception, doesn't matter if it's in the industry or in education, or you have to adapt to a specific task. And the best performance are the ones that are overfitting to that environment, that task, right? You will get the best there. Of course, this is not about generalization. It's not about, oh, if I can solve recognizing an apple to pick it up in CYBATHLON, then I will be better outside. No. But it's only for that task, right? Then what I would say is that even if you don't have the real data where you are going to compete, you have to try to be as close as possible. And if you are able to use that data as close as possible, combined with these pre-trained models, then you will perform decently well.
Maybe a related question. If you studied the racist rules book quite good, you had a look into it. Are there specific tasks that you would say there are methods you can very quickly apply, but you don't see them being applied in assistive technologies so far? Are there very straightforward solutions that you would say for this and that task, yeah, this is easy, we would do it, this and that? And another question in the other direction, where do you see the highest potential to improve performances in CYBATHLON tasks by innovating new methods for a specific task? So where is it straightforward and where is a lot to do? And I'm not sure if you have every task in mind, but maybe you have an example.
I mean, there are probably techniques that are straightforward to use. Let's say, when obstacle avoidance, navigation obstacle avoidance, get out of the competition just by avoiding obstacles. you can use any technique that give you dense enough to say, like, to drive and avoid the obstacles. They are straightforward to use, to apply there, but there is still an engineering work to make it work there. Because those are developed in a general setting of robot moving around, right? And then if you bring it to an agent that is perceiving and have to tell the user how to do it, there is a lot of engineering just to say, how do I use that, specific for that task? Now, similar to the robotic vacuum cleaner, if we think at the beginning was random paths, very crude, like nowadays, very crude technology. And with time, with the feedback of the users, with the how it's being used, what are the problems, has improved a lot. Now you control from the smartphone, you see a map, you see what is the pattern, you say, don't go there, my cat lives there, whatever, right? And I think CYBATHLON will do that. With the feedback from the pilots, then you will improve the techniques that adapt to those people, like to this pilot, to this disability, or to the general human user interfaces, such that the technologies follow there. But at the beginning, you have to use it crude and try to adapt yourself. With time, the technology will catch up, hopefully.
Thank you. Maybe a last question. I liked your conclusions and your examples also with the snow. So the CYBATHLON competition development team also thinks about new tasks for the future. We try to make the scenarios less predictable, but still in a competition, in a fair competition way. So do you think it would help the researchers, the research advance, if the CYBATHLON competition team asks for more tasks where you cannot really predict the scenario? Should we introduce snow, for example?
Yeah, definitely. I think this is a step to go, but I guess it's one step at a time. And it's just, can we even solve these tasks where I'm telling you what is going to face? And once you do that, continue. Maybe the technology changed a lot, or maybe the technology just evolved incrementally. But just step by step. But yeah, it will help at some point if you just give it open in the scenarios.
Thank you.
Thank you very much. It was very nice having you here, and the lecture was very informative. Thank you.
Thank you all.
So this was actually the very first time that we organized this CYBATHLON lecture series, and therefore we would really appreciate to get your feedback. So if there's anything that you would improve next time, or anything that you liked in particular, please share it with us in the coming days. We will also send out a feedback questionnaire in the next weeks, so yeah, you can get back to us. Additionally, we would also encourage you to share any topics of interest that we didn't cover yet with us, so we can address them the next time. Last but not least, I would like to remind you that the CYBATHLON challenges are taking place next February. The challenges are a great opportunity to get to know the teams, as well as for the teams to test their assistive technologies for the very first time in a real-life competition. The big CYBATHLON event, so the global edition, is then going to take place a couple of months later in October. Thank you again for being here today, and we are looking forward to seeing you at the challenges.